Good day, students. In this clip, we're going to be going over an example on how to, actually two examples on how to find poles, discontinuities, asymptotes, and roots of rational expressions, okay? In this video, I'm going to be doing just the vertical asymptote, and in the subsequent clip, I'll go over how to find the horizontal asymptote, okay? So let's go ahead and write down the instructions for the notes. So what we're going to do, we're going to find the poles, discontinuities, discontinuities. The discontinuities include the removable and or infinite. So you're going to find the poles, discontinuities, vertical asymptotes, and roots of the given rational functions. Okay. All right. So let's go ahead and take a look at question number 1. Question 1, we have a function that's already nicely factored out for us. F of x equals x times x minus 5 times x plus 4 over x minus 3 times x minus 5. Okay? Alright, so let's go ahead and start by looking for the poles. Alright? So poles. Now if you want to find the poles, all you do is you simply set the denominator to 0 and solve. Okay, set denominator to 0. Okay, denominator is basically q of x. Okay, q of x is the denominator. Set it equal to 0 and solve. Alright? So what's the denominator here? The denominator in this rational expression is x minus 3 times x minus 5. Okay? So what we're going to do is set it equal to 0. And to solve this, we'll simply use the zero product property. The product of these two quantities is 0. Here x minus 3 is 0, or x minus 5 is 0. Okay? So if you solve this, this one you just add 3 to both sides. You have x equals 3 as your first pole, and this one you add 5 to both sides, and then you have x equals 5 as your second pole. Alright, so your poles are x equals to set 3 and 5. Okay, so there you have it. Alright, now next we're going to look for are the discontinuities. Okay, the discontinuities. So write that down, discontinuities. First of all, we're going to list all the discontinuities, then we're going to separate them into the removable and the infinite, okay? So what are the discontinuities here? Guess what? The discontinuities as a whole are the same as the poles, okay? So your discontinuities are going to be x equals 3 and 5. Alright? So those are discontinuities. Now out of these discontinuities are could be a combination of 2 or just 1. Alright, so the question is, which of them do we have removable discontinuities here? So removable discontinuity. So to find the removable discontinuity, what we do is we rewrite the entire problem, copy down the problem again. The original problem is f of x equals x times x minus 5 times x plus 4 divided by x minus 3 times x minus 5. Now any factor that we can cancel out, that will be the one that gives us the removable discontinuity, okay? So you notice that I can reduce x minus 5 and x minus 5 on the denominator here. And the numerator, guess what? That discontinuity that I just removed is the removable discontinuity. Okay? So, so let's go ahead and solve it. So it's going to be, what we cancel out is x minus 5 equals 0. So to solve that, we simply add 5 to both sides. And you have x equals 5. Alright? So your removable or point. Another word for removable discontinuity is point. So okay, so removable or point discontinuity is x equals 5. So this 5 in the set of discontinuities is removable. Alright? So the next discontinuity that we're going to look for is the infinite. Okay? You might be able to guess what the infinite discontinuity is. So infinite discontinuity. So if you look at what we just reduced, the factor that did not get cancelled out, that one is the infinite discontinuity, or the root that, the pole that didn't get cancelled out. You notice there are two poles. This one is removable, this one is not removable. So guess what? That is your infinite discontinuity. So to get your infinite discontinuity, the one that isn't cancelled out, x minus 3, set it equal to 0. Solve by adding 3 to both sides. And I have x equals 3. And this is your infinite discontinuity. Right? So your infinite discontinuity is x equals 3. Okay? So remember, when you combine your infinite and removable discontinuities, they both combine to give you your discontinuities or your poles. Okay? Alright, now we're going to go ahead and find the vertical asymptote. So let's write that down. Vertical asymptote. Vertical asymptote. Okay. Alright, so the vertical asymptote is basically a vertical line on the graph where the graph approaches but never really crosses. Okay? So your vertical asymptote, guess what, is exactly the same as your infinite discontinuity. Okay? So same as infinite discontinuity. Okay? So what's the infinite discontinuity? X equals 3. So guess what? Your vertical asymptote is going to be the same thing, because they're one and the same. X equals 3. So you don't have to do any work for vertical asymptote. Alright? Okay, now the next thing we're going to look for are the roots. The roots of your polynomial function. Okay? Roots. So to find the roots, what you're going to do, we're going to rewrite the problem, reduce it, and then set the numerator to 0. Okay? Alright, so what we're going to do is reduce and set numerator equal to 0. Alright? So let's go ahead and do that. So we're going to rewrite the original problem. The original problem is f of x equals x times x minus 5 times x plus 4 divided by x minus 3 times x minus 5. Now the reason why we're reducing is because if I reduce this factor and this factor right here, even though it shows up in the numerator, is not a root because it's removed. It's a removable discontinuity. Okay? So you reduce it first, and what you have left, we're going to be left with x times x plus 4 over x minus 3. You set the numerator this time. The reduced numerator equal to 0. Okay? So you set the numerator equal to 0, x times x plus 4 equals 0, and then we solve. The reason being that when you cross multiply this equation, the denominator disappears because it's been multiplied by 0. Okay, so to find the roots, you reduce, set the numerator to 0, and then you solve. So to solve this using the zero product property, we're going to have x equals 0, or x plus 4 equals 0. This is already solved. To solve this, you subtract 4 from both sides. You have x equals negative 4. So our roots for this problem are negative 4 and 0. Okay? So there you have it. Alright, let's go ahead and try another problem. This one will be slightly longer because it's not in its reduced form. So let's write down question number 2. We're doing exactly the same procedure as the initial problem, okay? So for this one, we have f of x equals x to the third plus x squared minus 6x divided by x squared plus 2x. Okay? Alright, so before, I don't know what can be factored out or not, what can be reduced. So what I have to do is I have to factor the numerator and the denominator. In this factored form, it's easy to tell what factors can reduce or what factors cannot be reduced. Okay? So what I'm going to do, I'm going to extract the numerator, factor, and then the denominator and factor. Okay? So let's start with the numerator. The numerator is given by the polynomial, cubic polynomial, x to the third plus x squared minus 6x. Is there anything common that I can extract from this polynomial? Well, let's see. If I break it down into x times x times x plus x times x minus 2 times 3 times x, you can clearly see that x is common. So I can extract an x from all three terms. So we're left with x times x squared plus x minus 6. Okay? Now, how do I factor this quadratic trinomial in this parenthesis? Well, I can use my x game, right? The x method or the AC method to factor that out. So I make my little x right here. AC in this problem is negative 6 and B is 1. What two numbers work? We can use 3 and 2, negative 2. Okay? That goes into the center, so we have x times x squared plus 3x minus 2x minus 6. So now we're going to partition it down the middle and factor right group. Okay? Alright, so this x on the exterior stays there. We're just focusing our attention on factoring the inner quantity. So we're going to have x times x plus 3 times x minus 2 times x minus 2 times 3. And then we close down. Okay? Alright, now the left side of the partition in the parentheses, I can take out an x. And on the right side of the partition, I can take out negative 2, right? So let's see what that looks like. So if I reduce that, if I factor that, I'll bring out this x. I'll have x times x plus 3 minus 2 times x plus 3, like that. Okay? So we can see these two quantities are identical, which is perfect. So I'm going to bring down this x, and then x plus 3, the identical quantities, factor out as 1, and you're left with x minus 2. So put that in its own parentheses, like that. Okay? So there goes the factored form of the numerator. So f of x can be written as x times x plus 3 times x minus 2. Okay? Now we're going to shift our attention to the denominator and see if we can factor it. Okay? Alright, so our denominator is denominator. Let's write that down. Denominator. Our denominator is x squared plus 2x. So we're going to break this down into x times x plus 2 times x. So what can I factor out here? I can take out an x and an x. Alright, so if I take out an x, I'll be left with x plus 2. That goes into the denominator. We have x times x plus 2. Okay? Alright, now we have the reduced form. Now we can start looking for the relevant components. Alright? So the first thing we need to look for is the poles. Alright? Remember, the poles is what you get when you set the denominator to 0 and solve. Okay? So let's make that side note here. Set denominator to 0. Okay? Alright, so to do that, we're just simply going to take the denominator q of x, which is x times x plus 2, equals 0, and then solve. Okay? To solve this, use the zero product property, x equals 0, or x plus 2 equals 0. This has already been solved, so this one can be solved by subtracting 2 from both sides. So you have x equals negative 2. So our poles are given by x equals negative 2 and 0. Alright? Okay. Now let's talk about the discontinuities. Okay, so let's write that down, discontinuities. Discontinuities. You have to remember that the discontinuities are exactly the same as something we already know, namely the poles. Okay? So your discontinuities in general, combined discontinuities are negative 2 and 0. Why? Because it's basically the same as poles. Okay? Another word for discontinuities are the poles. Alright, now that we have our discontinuities, we have to further classify them into removable and infinite. Okay? So let's rewrite the original problem. Oh wait, wrong color. The original problem is f of x equals, the factored form is what we want because I want to know what cancels out and what doesn't. Okay? F of x equals x times x minus 2 times x plus 3 divided by x times x plus 2. Okay? Now, whichever factor gets cancelled out or removed, that is going to be our removable discontinuity. So is there any factor that any of the poles that I can cancel out or reduce? Absolutely, the x, right? So x goes here once, and x goes here once. Alright? So that factor that got cancelled out is your removable discontinuity. Alright, we have two discontinuities here, so you can clearly see that that 0 is a removable discontinuity. So let's write it down. Removable discontinuity, let's write removable disc, is x equals 0. There you have it. Alright? Okay, now the next thing we need to find is the infinite discontinuity. Okay? Infinite discontinuity, you might already guess what it is. The discontinuities have to be either removable or infinite, right? So we already know that the 0 is removable, so what do you think the infinite will be? Well, let's see. Infinite discontinuity. To find that one out, all we just simply do is take a look at the factor or the pole that did not get cancelled out in the reduction form, okay? So if you take a look at the original function that we had, we notice this got cancelled out, x plus 2 didn't get cancelled out. So that tells me that will help me find the infinite discontinuity, okay? So what I'm going to do is set that factor to 0, x plus 2 equals 0, and then solve. Okay, subtract 2 from both sides, and you're going to end up with x equals negative 2. You must have already guessed that, right? Because if this one is if 0 is removable, then the other one has to be the infinite discontinuity. Okay? So there goes your discontinuities further classified into removable and infinite. Now what we're going to do next is look for the vertical asymptote. Okay? So what is your vertical asymptote? Vertical asymptote. It is that horizontal line that the graph cannot cross. So your vertical asymptote is exactly the same as an infinite discontinuity, so it's simply going to be x equals negative 2. Okay? So there you have it. Now last but not least, we're going to look for the roots of our rational function. So to find the roots, we're going to take the original function, reduce it, and set the numerator to 0. Okay? We have to reduce because we have to take out the removable discontinuities because they cannot count as roots, okay? So there goes the original problem. Remember, we're shifting our attention to the numerator here, but we have to reduce first, okay? So this is the original problem. Now what can I reduce from here? I can reduce the x's. So x goes here 1, and x goes here 1, okay? So now I set the numerator after reducing to 0, x minus 2, and x was 3, equals 0. Now using the zero product property, I know that x minus 2 is equal to 0, and x plus 3 is equal to 0. So to finish this off, just add 2 to both sides, x equals 2. Subtract 3 from both sides, x equals negative 3. So that tells me that the roots of my rational function is given by negative 3 and 2. Okay? So there you have it. So thanks so much for taking the time to watch this video. Please subscribe to my channel just by clicking up here, or you can share this with your friends via Facebook or Twitter. More videos can be found on modularserve.com. Thanks again and have a wonderful day.